And so now we go for the next talk, which will be basically the video recorded. So it is about a computational study of constraints programming approaches for RCPSP with autonomous learning effect. We will start the video. So,
hey, my name is Alessandro. I will present the results of a research project that we did together with Jordan Ticktin, former graduate student, and Thomas Vossen from the University of Colorado Boulder. It's about resource-constrained project scheduling and how autonomous learning effects can be integrated into this scheduling model. We're going to motivate the work that we did first, then define the model that we developed and show you which solution methods we tried, and give you the results of a computational study and conclude afterwards. Let's talk about the construction industry for a little bit. So an apartment complex, for example, that needs to be constructed. Project scheduling is what really helps project managers here. Let's say that we're given the specifications of the building, and one step further, we already know what the individual jobs are that need to be performed to get this thing constructed. Then in project scheduling, what you want to do is you want to come up with a schedule such that you can maximize the efficiency of the project, and that means you want to minimize the make spend, so get that done as soon as possible, while certainly taking care of all the requirements that are given by the nature of the construction project itself. Let's look at one job that is the flooring on each of the levels. Certainly, you can gain experience by completing a floor, and this is just learning by doing, which is well known, is happening. And what we say is that if you have to do two different flooring jobs on two different levels, then they're similar, and therefore when doing them in parallel, you're less efficient than when doing them in sequence. If you do them in sequence, then you're basically gaining efficiency through the experience that you obtained in your first job of this kind. We say that there's two assumptions. The assumptions are that the knowledge gained in your first floor or at your first floor is transferable to the job that you're doing afterwards. So there's an efficient knowledge transfer procedure in place. You could also say that it's the same workers that work on the job, so they did it and therefore carry the knowledge with them. And we also say that a job can only learn from one other job that might be scheduled to be executed prior to it. The model that we developed is based on the resource constraint project scheduling problem, short RCPSP. The RCPSP itself comes with jobs that all have a fixed duration. There is precedence relations provided, and every job consumes resources of one or multiple resources per time period it is executed. And these renewable resources are given at a certain limit during every period. The constraints come from these precedence relations and from the resource limitations. The objective, standard objective that we're looking at is minimizing the project make spend. To the left here, you see a typical precedence network, and in the center now a representation of an optimal schedule. I think it's 30 jobs here in the form of a Gantt chart. So in every unit here, the resource limitations are respected regarding the jobs that are active in that unit, and also every precedence relation is fulfilled here in the schedule presented. This is a small example on this slide for an RCPSP. To the upper left, you can see the precedence network and also the durations of the jobs, and the lower Gantt chart shows us an optimal schedule for this tiny problem. To the right, we have the details that we're maybe not interested in right now. The make spend turns out to be 12 at best. And what we do, we extend this model. We now allow learning of selected jobs, and we call this model the RCPSP plus L, so plus learning. And it comes with additional information. You see this additional network in the center. It's the learning network. And the learning network tells us that specific jobs can be reduced in duration when scheduled after teaching jobs that basically provide the necessary experience for the benefit. An example here is job 5 and 4. So if 5 is scheduled after 4, then 5 can be reduced in duration by 2 units. 5 originally is 4 units long, but then could be reduced to 2 units. And if we consider this flexibility, then an optimal schedule is basically yielding us a project that is only 9 time periods long. So a benefit in overall project duration of 3 time periods. And the jobs learning here are only job 5 and job 6 because scheduled after 4 and 7 respectively. This is our new model that we'll be using here during this work. The solution approaches that we developed are based on constraint programming formulations of the RCPSP. And so a known efficient formulation for the RCPSP is given here. It's based on interval variables. It's a formulation that's expressed for CP optimizer, iLog CP optimizer. It has fixed durations, meaning that the lengths of these interval variables are specified by the durations of the jobs. A cumulative expression helps us respect all the resource consumptions over the horizon, and regular precedence constraints here make sure that the precedence relationships are respected. We minimize the end time of the terminal job. Based on this formulation, we derived a first formulation for our learning-based RCPSP, and we added the 2 implications that if the precedence is respected, then the time that the successor job takes is reduced. And if not, then the original duration is used. Another formulation is based on a dynamic expression in which we say that the length is directly expressed by the original length of the corresponding job minus potential reduction, and the reduction only takes place if the Boolean expression that decides whether the precedence is respected is true or false. This is formulation F2. There's a third formulation that we used based on multimode. Multimode is a concept that is commonly used in RCPSPs to express that a job can be executed in different modes, different ways. We here represent 2 different modes for a job as the regular mode, in which no learning takes place for a job, and the alternative mode, which is the actually beneficial learning mode, which is reduced in duration. We relate here the different modes and their presences by the precedence constraints to express it in the formulation. We did lower bounding and upper bounding. We said that we want to try out a couple of combinations of relaxed models that could give us lower bounds. So when optimally solving these, we can basically derive valid lower bounds. We did work with the reduced durations only, giving us here something like the RCPSP minus, that's how we call it. We dropped the precedences, we dropped the resources, and changed the duration, a bunch of different combinations.
Okay, so apparently there seems to be a problem with the slides in the video, if I understood correctly. So there was a request from the author if we could take over live.
Yeah, that will be fantastic. Unfortunately, somehow the slides got stuck. I'm not sure what happened there. I didn't notice that when submitting the presentation. So I would continue here lively if that's okay for you.
Yes, I think you have the right to share.
I have. Thank you very much. So, yeah, I presented basically, let me quickly wrap up this. I presented 3 different formulations. Formulation number 1 for this learning-based RCPSP, in which we have these implication constraints that we added here at the bottom. And that was our first start how to formulate this problem. And in a second formulation, formulation number 2, what we did is, what we did is we expressed that dynamically, meaning that the length of the interval variable is directly expressed by the original duration of the job minus the reduction in case that the precedence takes place, which is the multiplication through this Boolean expression here to the right. A third formulation was used in which we remodeled the whole thing as a multimode RCPSP. Multimode means that for every job, there is two modes, well, for most of the jobs. And these two modes correspond to executing the job either in the original duration or in the shortened duration. And these modes are then linked to the condition that the precedence needs to be met such that the reduced time mode can be used. These three formulations is what we used to solve the problem with. We also did lower bounding because we were aware that upper bounds might not be everything if optimality cannot be proven. We did a couple different combinations. We dropped the precedences, dropped the resources. We looked at only reduced durations without actually tying them to the requirement that the precedence for learning needs to be met. And when finding optimal solutions to these problems, they all correspond to added lower bounds for the make span. We also noticed that if you simply solve the RCPSP with its original durations, then whether optimal or not, any schedule for that will yield an upper bound for the RCPSP plus L problem. All these models that we used for lower bounding and upper bounding can be expressed using the RCPSP plus L because they're special cases of that. So we can use formulations 1 through 3 for that. Additionally, we added a lower bounding technique that's known as destructive lower bounding. It is effective for RCPSPs, and it is an iterative procedure in which we try to prove that a certain lower bound can be destructed or not. I'm not going into the details in here. Basically, it requires the sequential solution of constraint programming formulations to detect infeasibility. This is the basic principle. The main message here in this talk, in this project, is our computational results. We did an extensive study using a basic computer setup. This is just a regular laptop that ran for a couple of weeks, actually. And we added a couple of pre-processing techniques that also I'm not going to explain in detail here. And we generated over 100,000 test instances. The reason for that is that initially we had really no idea what the impact of learning reduction values and the number of jobs that can learn is. And so we expanded that as far as possible. And then now we know a little bit more that we had results for that. Based on PSP-lib instances, 30 jobs and 120 jobs, the CP solver is iLog CP optimizer in version 12.9. We first tried to isolate the or a formulation that works best for our setup, and we found out that in terms of number of optimal instances, in terms of average solve time for the optimally solved instances, and in terms of optimality gaps for the not optimally solved instances, formulation number 2 was outperforming the other formulations. We ran that on the 120 job instances, which means like 65,000 instances. So we did continue with formulation F2, and F1 and F3 were practically out of the game. When looking at our bounding approaches, we found out that not all these, let's say, submodels are easy to solve. The project scheduling problem itself obviously is easy to solve. You could polyomally solve it with a dedicated just by topological sorting. If you add the learning also, these are easy problems. But once resources and precedences come into play, all these bounding models were difficult to solve. Not more than 50% of them could be solved to optimality, and therefore I then yielded a valid lower bound. The lower bounding, long story short, the most effective was the destructive lower bounding. We got, this is the upper box plot here. So this is basically the relative lower bound with respect to the best upper bound obtained. Shortly followed by the lower bound that was provided by CP Optimizer. That's something that surprised us a little bit. So constraint programming is not necessarily, at least we were not aware that the lower bounding capabilities are that strong. And we tried it with different versions of CP optimizers and have the feeling that also this got much better during the recent years. When talking about the upper bounds, then certainly formulation number 2, so our basic CP formulation did the job well. The other approaches that we had could not really help here at all. Starting with our first formulation, F1, to where we got with destructive lower bounding and the best formulation, F2, we obtained this progress that is shown in these 2 box plots to the upper right. The optimality gaps were notably reduced. And this is basically the little diagram that shows what our efforts in testing and also developing were worth regarding the overall solution capabilities. We did an analysis of the model. We're not only interested how to solve these problems, we're interested what's the behavior for these models. Let's say on a restricted horizon, just looking at the test instances that we generated, and the 30 job instances could all be solved to optimality. That's why we used those instances to understand what the learning potentials are, or what, let's say, the make spend potentials are. So let me quickly explain what this diagram shows. On the x-axis, from left to right, we increase the number of jobs that can learn, and the y-axis, so from low to high, means how much percent of the non-learning model make spend are we achieving? So basically, the more down you go, the better your overall project make spend will be. And then these different colors show different learning intensities, meaning that 0.9 stands for a job that originally was 10 units long, now is only 1 unit long, if capable of learning. So if you add a lot of learning and you let them learn hard, then what you can get is a reduction up to 50% in make spend. This is an average over many instances. And similarly, if you add a lot of learning opportunities, but let them learn only little, then there's, in this case here, 7% of make spend reduction potential. It's near linear what we observed. So that is something that certainly instance dependent, but gave us an idea of what potentials can be found here in this new model. The utilization of learning, so how many jobs that could learn did actually learn. There's a similar chart here, goes up to 50%, 50% in the case that you let them learn a lot and let many of them learn, 35 in the case that they only get a little bit shortened in duration. I want to conclude by saying that what we did is a few things. We defined this new RCPSP with learning features integrated, autonomous learning features. We derived a couple of formulations using constraint programming and developed bounding techniques. The extensive computational study is what gave us part of our results. And our results are that there is a significant make spend reduction potential in using autonomous learning in project scheduling, in resource constraint project scheduling. And we see that this new model is not really harder than the RCPSP itself. So the integration of these features does not bring you significant computational disadvantages. The RCPSP being NP hard and computationally very challenging already, I mean, is a problem that I'm not going to talk about. Destructive lower bounding is a good procedure that is also easy to implement, that you can add if you want to tighten your optimality gaps for not optimally solvable instances. And in the future, one could, well, classically, one could do a little bit of math programming and trying to formulate that problem first. I think that would be a good challenge, or maybe develop a couple of heuristics that specifically tackle the learning part that is new here in this model. What we think is even more interesting is study-related learning concepts. Our learning concept is only a starting point to integrate learning capabilities into the RCPSP and project scheduling in general. And it would also be interesting to see how real-world instances can be solved or not. I'd say that they could be much easier, but how does that actually then look like? Something that we find interesting. Thanks a lot for your attention and for your flexibility for having this presentation, half virtual and half virtual. Thank you.
Okay, thank you. Thank you. I think we are running out of time. So basically, I suggest that people just after the session may ask you some question, but now we have to go for the third talk.